Right now, you're hurtling through space at 600,000 kilometers per hour, along with the Sun, which is racing around the supermassive black hole at the center of the Milky Way. Today, we'll journey from Earth to its edge, through stellar graveyards, colossal gas nebulae, and stars that are born and die before our very eyes. Want to see a real galaxy? Then buckle up. We're beginning. Our journey begins here on Earth, but it's important to remember that our planet is far from static. Currently, our entire solar system is moving through space at 108,000 kilometers per hour, significantly faster than any rocket ever built by humanity. Some might believe we're simply orbiting the Sun peacefully, but that's just a small part of the grander picture. The Sun itself carries us along on a much larger and more dynamic voyage. Imagine our solar system as a speedboat racing across a boundless ocean. In this analogy, the Sun is the boat, and all the planets are its passengers, carried through the cosmic expanse. We're not just aimlessly drifting, we're following a precisely defined trajectory around the center of our galaxy, completing one full orbit every 230 million years. It's worth noting that the last time Earth was in this exact spot in the galaxy, dinosaurs didn't even exist yet. However, there's another fascinating aspect to our motion. As we race through the galaxy, we also oscillate up and down, much like that same speedboat hitting waves. Every 33 million years, our solar system passes through the Milky Way's flat disk, then rises above it, and later dips back below it. Some scientists hypothesize that these crossings might be responsible for mass extinctions on Earth. When we traverse the galactic disk, we encounter increased cosmic radiation, asteroid fields, and gravitational chaos. Imagine traveling through different neighborhoods of a vast metropolis. Sometimes we're in quiet suburbs, surrounded by empty space. Other times, we're rushing through bustling downtown areas, teeming with stars, gas clouds, and cosmic debris. Currently, we reside in one of the quieter regions, which might explain why life has been able to thrive on our planet. Most strikingly, we are not traveling alone. Our solar system is nestled within a colossal bubble of hot, diffuse gas, stretching over 1,000 light-years in every direction. This cosmic bubble was formed by the explosions of massive stars millions of years ago. Their powerful blasts swept away much of the dense gas and dust, leaving us in this relatively empty patch of space. Without this protective bubble, Earth might look entirely different. Dense gas clouds and intense cosmic radiation could have made life survival significantly more challenging. Essentially, we inhabit the aftermath of ancient stellar violence, drifting through a sort of cavern carved out by the death of stars. When we gaze at the night sky, we see the edge of this bubble in all directions. The distant stars we observe are mostly located on the far side of our cosmic neighborhood, shining through the thin walls of our protective shell. We are like passengers in a glass submarine, traversing the deep ocean of space. Our journey to the galactic center begins right here, in this quiet cosmic bubble. However, as we venture further from our solar system, we'll discover that our peaceful region is surrounded by forces and structures that dwarf anything we can observe from Earth. The first of these cosmic landmarks lies just beyond our protective bubble, in areas where gas and dust begin to coalesce, and new stars are born on a truly impressive scale. The bubble of space we're in has a name among astronomers: the local bubble. This cosmic cavern stretches over 1,000 light-years, and we drift within it like a speck of dust in a vast cathedral. However, this cathedral was carved not by creation, but by violence. Approximately 10 to 20 million years ago, a cluster of massive stars lived out their life cycles and met their end in this region of space. When stars with masses 8 times greater than our Sun reach the end of their existence, they don't fade quietly. They explode as supernovae, releasing more energy in mere seconds than our Sun will produce in its entire 10 billion-year lifetime. These weren't isolated explosions. They occurred repeatedly as star after star in this region met its violent demise. Each cosmic supernova explosion propagated outwards like an invisible tsunami wave, powerfully pushing gas and dust away from the epicenter of its colossal destruction. When several such monumental blasts occur in the same region over millions of years, they form what astronomers call a superbubble. Our own local bubble is one such gigantic cosmic cavity, still expanding outwards from those ancient, distant explosions. To better visualize this process, imagine throwing pebbles into the calm surface of a pond. Each thrown pebble instantly creates ripples that spread evenly in all directions. Now, imagine throwing dozens of pebbles into the same area repeatedly over a long period. The overlapping ripples would undoubtedly create a complex, dynamic pattern of waves and relatively calm sections. This exact scenario unfolded in space. Only instead of pebbles and water, we're talking about stellar explosions and the very fabric of space-time. The walls of our cosmic bubble are far from empty. They consist of superheated gas, with temperatures exceeding 1 million degrees Celsius, heated by those same ancient, powerful explosions. This gas is so incredibly diffuse that a single cubic inch contains far fewer atoms than even the best laboratory vacuum on Earth. Nevertheless, it emits X-rays, invisible to the human eye, but reliably detectable by sensitive space telescopes. We are not precisely at the center of this giant bubble. Our solar system is actually located closer to one of its edges, slowly drifting toward a region where the bubble wall gradually begins to thicken with cooler gas and dust. Approximately 5 million years from now, we will inevitably break through this protective wall and enter a much denser part of our galaxy. When this momentous event occurs, our solar system will face entirely new challenges. The thin bubble of superheated gas currently surrounding us acts as a kind of shield, effectively deflecting some of the cosmic radiation that would otherwise relentlessly bombard Earth. Once we leave this natural protection and enter denser regions of space, our planet's atmosphere will encounter a much greater influx of high-energy particles arriving from deep space. Some scientists seriously question whether this could potentially trigger significant climate changes or even provoke mass extinctions on Earth. For now, however, we continue our journey through this cosmic safe harbor, reliably protected by the aftermath of stellar death. The irony here is simply astonishing. The very explosions that could have completely sterilized any planets in this region millions of years ago now provide a buffer zone that allows life on Earth to thrive. However, our peaceful journey through the local bubble will soon lead us to something truly extraordinary. Directly ahead of us, precisely in the direction of our solar system's motion, lie stellar nurseries, gigantic cosmic cradles where new stars are born. Just 400 light-years from Earth, in the profound darkness of space, something truly magnificent is unfolding. Giant clouds of gas and dust are gradually collapsing under their own gravity. And deep within these cosmic cocoons, brand new stars are igniting for the very first time. The closest star-forming region to us is so active that if our eyes could perceive infrared light, it would shine brighter than any star in our night sky. These amazing stellar nurseries are called the Orion Molecular Cloud, and it's a veritable factory for producing suns. Imagine a cloud of gas and dust so colossal that it takes several years for light to travel from one edge to the other. Now, envision this cloud slowly contracting like a giant invisible hand squeezing a sponge. As the cloud shrinks in volume, it heats up. When its core becomes hot enough, nuclear fusion begins and a new star ignites its glow for the first time. However, the birth of a star is far from a gentle or calm process. When a new star flares to life, it ejects powerful winds of particles at hundreds of kilometers per second. These stellar winds carve out immense bubbles and caverns in the surrounding gas cloud, creating structures resembling cosmic sculptures. Some of these newborn stars are so massive and energetic that they illuminate entire sections of their parent cloud, forming luminous nebulae visible from thousands of light-years away. This process takes millions of years, which might seem long until you realize that most stars will shine for billions of years. It's like watching a flower slowly bloom, only this flower is larger than our solar system and will burn brighter than 1,000,000 suns. Not every clump of gas becomes a star. Some only partially collapse and turn into brown dwarfs, so-called failed stars that glow faintly in the infrared. Others are torn apart by the powerful winds and radiation from their more successful neighbors. What makes this process even more remarkable is that stars are not born in isolation. When a gas cloud collapses, it typically fragments into dozens or even hundreds of pieces, each of which subsequently becomes its own unique star. These celestial siblings, these stellar brothers and sisters, begin their existence grouped in close communities, sharing the same cosmic neighborhood. Over many millions of years, they gradually disperse as the powerful gravity of the rest of the galaxy relentlessly pulls them in different directions. Our own sun, the central luminary of our system, was born precisely this way, in a star cluster containing thousands of other stars, approximately 4.5 billion years ago. These stellar relatives are now scattered throughout the boundless galaxy. Identifying them is an impossible task, as they have drifted so far from their birthplace. Somewhere out there, among the hundreds of billions of stars in the Milky Way, lie the long-lost brothers and sisters of our Sun, awaiting their discovery. The star formation process, actively occurring in nearby regions of space, offers us a unique opportunity to glimpse our own origins. Every chemical element present in your body, with the exception of hydrogen and helium, was forged in the hearts of stars and dispersed into space at their demise. The calcium strengthening your bones, the iron flowing in your blood, the oxygen you breathe, all originated from stellar furnaces that burned billions of years ago. You are literally made of stardust, gathered from the ashes of cosmic giants. These stellar nurseries, these cradles of life, are just the beginning of our thrilling galactic journey. As we move further from Earth, we will encounter a larger structure that encompasses these star-forming regions. Our solar system does not reside in some random part of the galaxy. We are embedded within a structure so vast that early astronomers had no inkling of its existence, unable to comprehend its scale. The Orion Arm, also known as the Local Arm, is a minor spiral arm of the Milky Way galaxy that extends for thousands of light-years in both directions from our current position. We are not merely moving alongside this grand structure. We are actually woven into its fabric, an integral part of it. Imagine the Milky Way galaxy as a colossal hurricane viewed from deep space. The bright spiral arms you see in photographs are like storm bands of clouds. Except instead of water vapor, these arms contain stars, gas, and dust. Most galaxies possess 2 or 4 major spiral arms, but they also have smaller arms and spurs branching off the main structure. The Orion Arm is one of these less significant branches, but it nonetheless plays an important role. For many decades, astronomers believed we resided in a tiny spur connecting 2 major arms. However, recent observations have revealed something astonishing, something truly remarkable. The Orion Arm turned out to be significantly larger and more substantial than anyone had anticipated. It stretches for over 20,000 light-years, making it a significant galactic feature in its own right, not merely a minor detail. We do not live in a cosmic backwater, nor on the fringes of the galaxy. We are part of a major galactic thoroughfare, a bustling pathway. This spiral arm contains some of the most famous objects in our night sky. The bright stars of the constellations Orion, Perseus, and Cygnus all belong to our local arm. So too do many of the stellar nurseries where new stars are born, including the vast molecular clouds we just explored, these cradles of the stellar world. The arm functions like a gravitational river, guiding gas and dust into dense streams where intense star formation can occur. However, spiral arms are not permanent, immutable structures. They are more akin to traffic jams on a cosmic highway, temporary conglomerations. As material orbits the galaxy, it bunches up in certain regions, creating the illusion of spiral patterns. Stars and gas clouds flow into the arms, spend some time there, and then flow back out into the spaces between the arms. Our solar system has likely drifted into and out of spiral arms several times during its long journey through the galaxy, making this back-and-forth motion. The density difference between the arms and the spaces between them significantly impacts star formation rates throughout the galaxy. When gas clouds enter a spiral arm, they are compressed by increased gravitational forces and higher densities. This compression can trigger the collapse of gas clouds, leading to the formation of new stars. Then, as massive stars form and eventually explode as supernovae, they can disrupt nearby star formation, or conversely, induce even more stellar births, stimulating a new cycle. Currently, we are located roughly halfway between the galactic center and its outer edge, in what astronomers call the galactic habitable zone. This may not be a mere coincidence. Closer to the center, there's too much radiation and gravitational chaos for stable planetary systems to exist sustainably. Further out, there aren't enough heavy elements to form rocky planets like Earth. Our location in the Orion Arm places us in a cosmically ideal spot, a truly unique position. As we venture deeper into galactic space, researchers leave behind the familiar local arm to encounter far grander and more imposing structures that dominate the inner regions of the Milky Way. Be prepared for the numerical data presented next to radically transform the traditional understanding of motion. At this very moment, you are not simply sitting calmly, reading these lines. You are hurtling through space at a speed exceeding that of a rifle bullet, a jet fighter, and any other craft ever created by humanity. And this is just the initial stage of your cosmic displacement. At present, planet Earth rotates on its axis at the equator at a speed exceeding 1,600 kilometers per hour. This represents the first level of cosmic motion. Furthermore, Earth orbits the Sun at 108,000 kilometers per hour, carrying all its inhabitants with it. Most people are aware of these movements, yet they seem insignificant compared to the subsequent discoveries. The entire solar system rotates around the central region of the Milky Way galaxy at a speed reaching 827,000 kilometers per hour. Let that information sink in. Every second, you traverse over 225 kilometers of cosmic space solely due to galactic rotation. If it were somehow possible to be outside this motion and observe the solar system flying past, it would streak by an observer faster than the human eye can perceive a beam of light. However, this doesn't exhaust the entire picture. Our galaxy itself is also moving through space. The Milky Way is rapidly heading towards a massive cluster of galaxies known as the Virgo cluster at a speed exceeding 1.6 million kilometers per hour. In turn, the Virgo cluster is being pulled towards an even grander structure, dubbed the Great Attractor, at truly astonishing velocities. When all these multifaceted movements are summed up, it becomes clear that movement through the universe occurs at approximately 2.4 million kilometers per hour. It's worth pondering this magnitude. In the short time it takes to read this sentence, you have already traveled hundreds of kilometers through cosmic space, experiencing absolutely nothing. There's no cosmic wind in your hair, no sensation of acceleration. Movement through the universe happens at dizzying speeds. The only reason this motion isn't felt is because all surrounding space and objects are also moving in sync. This galactic motion carries consequences far beyond simply impressive numerical values. As the solar system orbits the galaxy, it encounters diverse cosmic environments. Sometimes it passes through the galaxy's spiral arms, where active star formation and elevated radiation levels are observed. At other times, it flies through quieter regions between the arms, as is currently the case. The solar system's orbital speed means that one full revolution around the galaxy takes 230 million years. This time interval is defined by astronomers as a galactic year. Since its formation, Earth has completed approximately 20 such galactic years. The last time the planet was in this specific position in its galactic orbit, the most complex life forms on Earth were merely simple marine creatures. Dinosaurs, mammals, and, of course, humans. All these species evolved during the solar system's current journey through the galaxy. The Milky Way's rotation is not uniform. Stars closer to the galactic center move at higher speeds, while luminaries on the outer fringes move slower. It is this differential rotation that ensures the preservation of the galaxy's spiral structure. If all its components rotated at identical speeds, the spiral arms would quickly wind up and disappear within a few 100 million years. As we delve deeper towards the galactic center, we will encounter regions where these cosmic speeds become even more extreme, and where the effects of galactic rotation give rise to some of the universe's most peculiar phenomena. Among the shining stars that illuminate the night sky lurk so-called cosmic dead. Scattered throughout the local region of the galaxy, these objects are the remnants of luminaries that have long exhausted their nuclear fuel, leaving behind structures so unusual they seem like something out of pure science fiction. These stellar corpses are invisible to the human eye, yet they are ubiquitous. Some of them are among the most dangerous objects existing in the universe. The most common inhabitants of these stellar graveyards are white dwarfs. These are extremely dense, superheated cores that remain after stars comparable in mass to the Sun complete their life cycle. A white dwarf can contain approximately 60% of the Sun's mass within a sphere comparable in size to Earth. This means that just 1 teaspoon of white dwarf matter would have a mass equivalent to that of a car. The closest white dwarf to Earth is only 8.5 light-years away, making it one of our nearest stellar neighbors. In their initial state, white dwarfs possess an astonishing temperature, exceeding 100,000 degrees Celsius, but over billions of years, they gradually cool. Some of the oldest white dwarfs in our galaxy have been cooling for so long that their current temperature is lower than that of our Sun's surface. These ancient stellar remnants are like cosmic time capsules, preserving invaluable information about stars that completed their life cycles during the universe's youth. However, white dwarfs are capable of a spectacular rebirth. If such an object has a companion star, it can steal matter from its partner, using gravitational attraction. When enough stolen material accumulates on the white dwarf's surface, it triggers a thermonuclear explosion known as a nova. This explosion sheds the accumulated material, and the process can repeat multiple times. Even more enigmatic are the neutron stars lurking in our galactic region. When a star with at least 8 times the mass of our Sun explodes as a supernova, its core can collapse into something almost unimaginable. A neutron star is so incredibly dense that a sugar cube-sized piece of its matter would weigh 6 billion tons. This exceeds the mass of Mount Everest. The entire star, containing more mass than our Sun, is compressed into a sphere only about 20 kilometers in diameter. Some neutron stars spin hundreds of times per second, emitting beams of radiation from their magnetic poles. If these beams sweep past Earth, we detect them as regular pulses of radio waves. These objects, called pulsars, are like cosmic lighthouses, possessing such astonishing timing precision that they can rival atomic clocks. The fastest spinning known pulsar rotates 716 times per second. The magnetic field surrounding neutron stars are trillions of times stronger than Earth's magnetic field. If a neutron star were placed where our moon is now, its magnetic field would erase the information from every credit card on Earth. Approaching it closer than 600 meters would be instantly fatal, as its magnetic field would disrupt the electrical activity of your nervous system. These stellar graveyards are not just cosmic curiosities. They are true laboratories for studying physics under conditions impossible to recreate on Earth. They help us understand what happens to matter under extreme gravity, high temperatures, and powerful magnetic fields. However, as astonishing as these stellar remnants are, they represent only a foretaste of what awaits us as we delve deeper into the galaxy. Leaving our local spiral arm and venturing deeper into the galaxy, we encounter something that dwarfs our entire cosmic neighborhood. The Perseus arm is one of the Milky Way's major spiral arms. It's a galactic superhighway, teeming with far more stars, gas, and cosmic activity than anything we've seen so far. It's like transitioning from a quiet suburban street to a bustling freeway. This massive structure contains some of the brightest and most energetic stars in our galaxy. While our local arm is home to relatively modest stars and star-forming regions, the Perseus arm harbors stellar monsters. Stars here can be 50 or even 100 times more massive than our Sun, burning so brightly and hotly that they appear blue-white in our telescopes. These giants live fast and die young, typically burning out in just a few million years. The Perseus arm gets its name from the constellation Perseus, which lies in the same direction when viewed from Earth. However, this spiral arm extends far beyond what we can observe with the naked eye. It stretches for tens of thousands of light-years, coiling around the galaxy like a loosely wound spring. If you could shrink the Milky Way to the size of a dinner plate, the Perseus arm would be one of the major lines you would see spiraling outward from the center. What makes spiral arms like Perseus so active? They are regions where the galaxy's density waves pile up gas and dust, creating ideal conditions for massive stars to form. Imagine it like a traffic jam on a highway. Cars accumulate in certain spots, slowly move through the congestion, and then spread out again on the other side. Gas clouds, much like large celestial bodies, also perform their majestic dance, orbiting the galactic center. Upon entering the spiral arms, they undergo powerful compression, which invariably leads to bursts of active star formation. The Perseus arm, one of the most prominent structures, is home to some of the most spectacular stellar nurseries known to modern astronomy. Among them, the Eagle Nebula stands out, famous for its towering, majestic pillars of gas and dust, within which new stars are born. These colossal pillars stretch for many light-years, their shapes carved by the intense radiation emanating from nearby massive luminaries. Another notable region, the Rosette Nebula, glows with a bright red light, sourced from ionized hydrogen gas, heated by a cluster of hot young stars at its heart. However, the Perseus arm is not only a cradle for new stars, but also an arena for some of the most dramatic and violent stellar deaths. When these colossal blue stars reach the final stage of their relatively short life cycle, they explode as supernovae, releasing energy equivalent to billions of suns. Such explosions are so powerful that they can be observed from other galaxies, millions of light-years away. Furthermore, these cataclysms eject heavy elements into interstellar space, enriching the surrounding gas with the building blocks necessary for the formation of rocky planets and, possibly, for life itself. Traveling through the Perseus arm can be compared to moving through a gigantic cosmic construction site. Wherever one looks, activity abounds. Stars are born, stars explode, gas clouds collide and merge, creating intense radiation fields capable of sterilizing any unprotected spacecraft. This place is simultaneously beautiful and deadly. As we continue our journey toward the galactic center, we are destined to confront even more massive structures and more extreme conditions. Imagine looking at the night sky and seeing not just individual stars, but entire cities composed of them, so densely packed that they resemble glowing clouds. As we delve deeper into the galaxy, we encounter star clusters that contain hundreds of thousands and sometimes millions of stars, all born from the same cosmic cradle. These stellar cities represent some of the most impressive and populous places in the Milky Way. The most massive star clusters in our galaxy are called globular clusters, and their age defies imagination. These spherical groupings of stars formed when the universe was still very young, over 12 billion years ago. A single globular cluster can hold up to 1 million stars, packed into a space of just a few hundred light-years. If Earth orbited a star at the center of a globular cluster, our night sky would contain thousands of stars brighter than Venus, transforming night into a shimmering twilight. Imagine the difference in density. In our solar neighborhood, the nearest star is over 4 light-years away. In the core of a globular cluster, stars can be separated by distances smaller than our solar system. If our Sun resided in such a crowded environment, we might have dozens of neighboring stars located closer than the planet Pluto. The gravitational interactions between all these stars would render planetary orbits chaotic and extremely unstable. However, globular clusters are not the only stellar cities in our galaxy. Scattered across the galactic disk are open clusters. These are younger groups of stars that formed relatively recently from the same gas cloud. The most famous open cluster, visible to the naked eye, is the Pleiades, also known as the Seven Sisters. This cluster comprises over 1,000 stars, all born within the last 100 million years from a single molecular cloud. Open clusters are, in essence, stellar nurseries that we can observe in action. Unlike ancient globular clusters, where star formation ceased billions of years ago, some open clusters are still embedded within the gas and dust clouds where they originated. We can watch new stars ignite while others are still condensing from the surrounding material. It's like observing a cosmic city under construction. These stellar cities do not exist forever. Over hundreds of millions of years, gravitational interactions with other stars and gas clouds gradually tear the cluster members apart. Stars are ejected from the group and become isolated wanderers, much like our Sun. Most open clusters completely dissipate within 1 billion years, scattering their stars throughout the galaxy. Star clusters serve as cosmic laboratories, allowing astronomers to test and refine existing ideas about stellar evolution. Since all celestial luminaries within such clusters form simultaneously and from the same initial material, they represent ideal natural experiments. Astronomers can compare the evolutionary processes of stars of different masses by studying cluster members that vary in size and weight. Some of the most massive star clusters within our galaxy are so densely packed with giant stars that they are dubbed superstar clusters. These unique regions contain dozens of stars, each 50 times more massive than our Sun, all crammed into spaces smaller than our solar system. The radiation and powerful swelling winds emanating from these cosmic behemoths create some of the most extreme conditions in the entire galaxy. As we delve further towards the galactic center, we will discover that these impressive star clusters are merely harbingers of the cosmic chaos that awaits us ahead. Between the stars stretches an invisible ocean. Most people tend to believe that cosmic space is empty, but in reality, it is filled with vast streams of gas and dust that move between the spiral arms, much like cosmic rivers. These interstellar currents are invisible to the human eye, yet they play a crucial role in shaping the evolution of our entire galaxy, transporting the raw materials necessary for star formation from one region to another. These gas flows are not randomly distributed in space. They follow specific patterns that arise under the influence of galactic rotation and gravitational forces. As the Milky Way rotates, differential rotation causes gas clouds to stretch and shear, leading to the formation of long filaments capable of extending for thousands of light years. Imagine this as stirring honey into a cup of coffee. The stirring motion creates spiral patterns and flows that follow the direction of rotation. The composition of these interstellar rivers tells the story of stellar life and death throughout the galaxy. A significant portion of the gas consists of hydrogen and helium, remnants of the Big Bang. However, mixed with them are heavier elements, formed within stars and dispersed by supernova explosions. Carbon, oxygen, silicon, iron, and dozens of other elements travel along these cosmic currents, gradually enriching various regions of the galaxy with the building blocks for rocky planets. Some of these rivers flow inward towards the galactic center, while others spiral outward towards the galaxy's edge. The inner flows feed the massive star-forming regions located near the galactic nucleus. The outer flows carry processed material from the crowded inner galaxy to the quieter outer regions where our solar system resides. Over billions of years, this circulation has gradually redistributed elements throughout the Milky Way. However, these are not gentle and steady flows. The interstellar medium is characterized by turbulence and chaos, stirred by stellar winds, supernova explosions, and the gravitational forces of massive stars and star clusters. Shock waves resulting from stellar explosions can trigger the collapse of nearby gas clouds, initiating new cycles of star formation. Other shock waves, conversely, can inhibit star formation by heating and dispersing raw material before it can condense. Temperature variations within these gas streams create a complex ecosystem of interstellar environments. Some regions contain hot, diffuse gas, heated to millions of degrees by supernova explosions. Other areas contain cold, dense molecular clouds, where temperatures drop to a few degrees above absolute zero. These molecular clouds are the nurseries where new stars form, but they constitute only a small fraction of the total interstellar medium. Magnetic fields permeating these gas flows add another layer of complexity. These fields, despite their incredible weakness by Earth standards, can guide the flow of charged particles and influence how gas clouds collapse to form stars. They also accelerate cosmic rays, high-energy particles that travel throughout the galaxy at speeds close to that of light. As our journey brings us closer to the galactic center, these interstellar rivers become more turbulent and energetic. Gas density increases, magnetic fields strengthen, and star formation rates sharply rise. We are approaching regions where the calm interstellar medium of our local neighborhood gives way to a cosmic maelstrom surrounding the galaxy's heart. The next major structure we encounter represents a dramatic increase in scale and a manifestation of violence. We have now reached one of the true giants of the galaxy. The Scutum Centaurus arm is the longest and most massive spiral arm in the Milky Way. This cosmic structure is so enormous that it spans over half of the entire galaxy. If the Perseus arm was a bustling highway, this is undoubtedly a superhighway, carrying the bulk of our galaxy's star formation and stellar activity. This massive arm gets its name from two constellations visible from Earth, Scutum and Centaurus. However, these tiny patches of sky barely hint at the true scale of this monumental structure. The Scutum Centaurus arm stretches for over 60,000 light-years, making it longer than the distance from Earth to the galactic center. It contains some of the most active star-forming regions in the entire galaxy, representing a true cradle for new luminaries. What makes this arm so special is its proximity to the galactic center. As one of the inner spiral arms, it receives a constant influx of gas and dust from the galaxy's central regions. This building material is channeled along the arm's entire length, creating an almost continuous chain of stellar nurseries and massive star clusters. The arm acts as a cosmic conveyor belt for star production, constantly replenishing our galaxy's stellar population. The rate of star formation in the Scutum Centaurus arm is astonishing. In some regions, new stars are born at speeds thousands of times greater than in our quiet local neighborhood. And these aren't just ordinary stars. The arm specializes in producing stellar monsters, luminaries with masses 50 to 100 times greater than our Sun. When these giants explode as supernovae, they can outshine entire galaxies for weeks, displaying their dazzling power. One of the most remarkable features of this arm is the Scutum star cloud, a dense concentration of stars visible to the naked eye as a bright patch in the constellation Scutum. This region contains some of the brightest known stars, including red supergiants. They are so large that they could engulf the orbit of Mars if placed at the center of our solar system. These stellar giants burn through their nuclear fuel so rapidly that they live for only a few million years before exploding, completing their short but brilliant cycle. The density of matter in the Scutum Centaurus arm creates a gravitational playground where massive stars and star clusters interact in complex ways. Stars can be ejected from clusters at high velocities, becoming runaway stars that race across the galaxy. Some of these stellar escapees move so fast that they eventually leave the Milky Way entirely, becoming lone wanderers in intergalactic space. But perhaps the most impressive aspect of this arm is how it channels material toward the galactic center. Gas clouds flowing along the arm's length eventually reach the central regions of the galaxy, where they encounter gravitational forces and conditions unlike anything else in the Milky Way. This feeding process has continued for billions of years, gradually building the massive structures we will encounter at the galaxy's heart. As we follow these gas streams deeper into the galaxy, we approach a region where the ordinary rules of stellar physics begin to break down. Gravitational forces become so strong and density so extreme that matter behaves in ways impossible anywhere else in our cosmic neighborhood. The next structure we encounter will challenge everything we think we know about how galaxies work. Hidden at the heart of our galaxy is a secret that astronomers have only uncovered in recent decades. The Milky Way is not merely a simple spiral galaxy. At its center lies a massive bar-shaped structure composed of stars and gas, invisible from Earth, but larger than anything we've encountered so far. This galactic bar is a hidden backbone that controls the flow of matter throughout our galaxy. Imagine the Milky Way from above, and instead of seeing neat spiral arms emerging from a circular center, you'd see something more akin to a cosmic dumbbell. The galactic bar stretches for over 27,000 light-years from end to end, making up roughly half the diameter of the entire galactic disk. This massive structure rotates as a single entity, spinning faster than the surrounding spiral arms. The bar at the galaxy's center formed billions of years ago through an astonishing process called bar instability. Over time, as the galaxy aged and stars settled into more circular orbits, gravitational interactions between them gradually began to align into elongated patterns. For hundreds of millions of years, these initial patterns continuously intensified until they took on the rigid bar-shaped structure we observe today. It's important to note that approximately 2/3 of all spiral galaxies possess similar bars in their central regions. However, this is not merely a static formation. The galactic bar functions as a cosmic pump, actively channeling gas flows from the outer regions of the galaxy directly toward its center through a process known as gravitational torque. As they orbit the galaxy, gas clouds encountering the bar's powerful gravitational field are deflected from their original circular orbits, shifting onto elongated trajectories that spiral inward. This phenomenon can be compared to water rushing down a drain, but with the significant difference that this drain spans 27,000 light-years. This powerful inflow of gas into the central regions of the galaxy has profound implications for its entire structure and evolution. The bar has continuously supplied building material to the galactic center for billions of years, contributing to the formation of the massive structures and extremely dense stellar populations we find there. Without this active pumping action of the bar, the central regions of our galaxy would be significantly calmer and much less active places. Furthermore, the bar significantly influences the movement of stars throughout the galaxy. Stars that approach the bar too closely can be gravitationally scattered onto entirely new orbits, sometimes being ejected either towards the galactic center itself or, conversely, into its outer regions. Our own solar system may well have experienced the bar's influence at various stages of its long journey through the galaxy. Although we are currently in a relatively safe region, significantly distant from the bar's direct impact, recent astronomical observations have revealed that the galactic bar is not a perfectly smooth structure. It contains its own complex spiral architecture, consisting of dense lanes of gas and dust that wrap around its entire length, resembling cosmic strands of deoxyribonucleic acid. These spirals within the bar represent some of the most active star-forming regions in the entire galaxy, continuously fueled by a fresh influx of material from its outer regions. The bar's rotation speed is finely tuned to maintain the galaxy's overall spiral structure. If it rotated too fast, or conversely too slowly, the spiral arms would either wind up too tightly or completely unwind within a few 100 million years. This delicate but crucial balance has kept the Milky Way's basic structure stable for billions of years. As we mentally follow the bar's gravitational channels toward the galactic center, we approach regions where the density of stars and gas reaches truly extreme levels. As we approach the inner region of the galaxy, the space between stars transforms into something almost unrecognizable. Here lurk molecular clouds so colossal that they dwarf entire solar systems. These are true cosmic titans, containing enough raw material to create millions of new stars. These are not the modest stellar nurseries we are accustomed to seeing in our immediate cosmic vicinity. These are the galaxy's heavy industrial zones, where star formation occurs on scales that are difficult to comprehend. The largest of these gigantic formations is named Sagittarius B2, a whole complex of molecular clouds located just 300 light-years from the galactic center. This single cloud alone contains enough material to form 3 million stars like our Sun. If you could somehow incredibly compress our entire solar system to the size of a marble, Sagittarius B2 would still be larger than a football stadium. The cloud is so massive that its colossal gravitational pull significantly influences the orbits of nearby stars. However, size is not the only characteristic that makes these clouds truly remarkable. The conditions within them are entirely unlike anything we can find in our quiet corner of the galaxy. Temperatures there plummet to just 10 degrees above absolute zero, making them some of the coldest places in the entire universe. At these extremely low temperatures, hydrogen atoms combine to form hydrogen molecules, creating a dense fog of gas and tiny dust particles. The chemical processes occurring within these clouds read like a cosmic cookbook. Over 150 different molecules have been detected in interstellar space. From simple compounds like water and carbon monoxide to complex organic substances that could potentially serve as building blocks for life. Some clouds contain a colossal amount of ethyl alcohol, enough to fill all of Earth's oceans. Others contain molecules that smell like raspberries or taste like rum. These grand aggregations of molecules do not simply float inertly in space. They are constantly subjected to intense stirring and heating by radiation emanating from nearby stars, powerful shockwaves resulting from supernova explosions, and the ubiquitous magnetic fields that permeate the entire galaxy. Such turbulence gives rise to a complex internal structure, characterized by dense cores, expanding shells, and dynamic flows of matter. These clouds can be compared to grand cosmic weather systems, possessing their own storms and unique circulation patterns. When individual sections of these clouds reach sufficient density, gravitational forces take over, and the collapse process begins. However, this collapse does not happen instantaneously. Different segments of the cloud collapse at varying rates, initiating a cascading star formation process that can continue for many millions of years. The most massive regions collapse first, forming giant stars that eventually explode, triggering further collapse in neighboring regions. The scale of star formation in these regions is capable of astounding the imagination. A single complex of molecular clouds can simultaneously give birth to thousands of new stars, forming colossal stellar associations that in their size surpass entire galaxies. Some of the brightest and most active star-forming regions in the known universe are fueled by molecular clouds located near galactic centers. As we delve towards the very heart of the galaxy, these molecular giants become even more extreme. Matter density increases, gravitational forces multiply, and star formation rates reach levels that could completely sterilize any nearby planetary systems due to colossal radiation emission. We are approaching the galaxy's central molecular zone, where the familiar rules and mechanisms of star formation entirely lose their power. Welcome to the most extreme and unique region of our galaxy. The central molecular zone is a gigantic ring of molecular clouds that encircles the Milky Way's center, and it is utterly unlike any other place we have ever explored. Here, just a few hundred light-years from our galaxy's supermassive black hole, the laws of physics are pushed to their absolute limits. It's a place where cosmic violence and star birth collide in ways that would be utterly impossible in any other part of the galaxy. The entire central molecular zone spans approximately 1,000 light-years, yet it contains as much gas and dust as the rest of the inner galaxy combined. This colossal amount of raw material is enough to form 10 million stars like our Sun. And all of this incredible amount of matter is packed into a region that constitutes less than 1% of the galactic disk's total area. If our local region of space has the density of air, the central molecular zone has the density of water. However, despite containing enough material for explosive star formation, this region is surprisingly quiet and calm. The star formation rate here is actually 10 to 100 times lower than it should be, given the available gas reserves. Something is preventing these massive molecular clouds from collapsing into stars, and astronomers are still actively trying to understand the reason for this phenomenon. The answer lies in the extreme conditions prevailing near the galactic center. Intense magnetic fields, heated by the supermassive black hole and thousands of massive stars, permeate the molecular clouds like invisible steel cables. These fields are strong enough to prevent the gravitational collapse of the clouds, hindering the usual cascade of star formation we observe in other parts of the galaxy. When star formation does occur in this region, it results in some of the most massive known stars. These stellar monsters can be over 100 times more massive than our Sun. They burn so intensely and brightly that they appear blue-white even from thousands of light years away. They live fast and die young, typically exploding as supernovae just a few million years after their birth. Temperatures in this region eloquently testify to cosmic violence. While the dense cores of molecular clouds remain cold, the spaces between the clouds are filled with gas heated to millions of degrees by shock waves from stellar explosions and energy emanating from the central black hole. This creates a bizarre environment where icy cold molecular gas exists just a few light years from plasma hot enough to strip electrons from atoms. In this region of space, magnetic fields possess power thousands of times greater than what is observed in our solar system. These colossal forces accelerate particles to unimaginable speeds, generating streams of cosmic rays that then disperse throughout the galaxy. Some of these high-energy particles eventually reach our planet, Earth, where their presence is detected by cosmic ray observatories as showers of subatomic particles permeating our atmosphere. The central molecular zone serves as a gigantic reservoir, accumulating gas and dust, which sometimes gets channeled even closer to the galactic center. When equilibrium is disturbed by gravitational instabilities or powerful stellar explosions, streams of matter spiral towards the supermassive black hole. This leads to bursts of activity that can be registered across all ranges of the electromagnetic spectrum. As we penetrate deeper into this cosmic maelstrom, we steadily approach the point of no return. Deep within the very heart of our galaxy, something pulsates, constantly sending out signals. Radio telescopes on Earth pick up a continuous stream of these messages emanating from the galactic center. These electromagnetic dispatches carry information about conditions that no human could ever experience firsthand. To reach us, these radio waves have traveled a distance of 26,000 light-years, bringing news from the most turbulent and violent corner of our cosmic neighborhood. These signals speak of continuous chaos. Unlike the stable radio emissions characteristic of ordinary stars, the galactic center broadcasts in bursts and flares, whose intensity can change within mere minutes. Sometimes the signal strength increases hundreds or even thousands of times, then subsides back to its usual level. These fluctuations represent the radio signatures of matter rapidly falling into our galaxy's central black hole, emitting its last electromagnetic distress signal before vanishing forever into its abyss. However, the central black hole is not the only source of radio emission in this bustling region. Dozens of compact radio sources are scattered throughout the galactic center. Each one is a kind of cosmic beacon, continuously radiating energy in all directions. Some have been identified as neutron stars, super-dense remnants of colossal stellar explosions. Others are stellar mass black holes, which are smaller siblings of the central monster and actively consume surrounding gas and dust. The most enigmatic radio signals emanate from long, thin structures known as non-thermal filaments. These cosmic filaments stretch for hundreds of light-years through the galactic center, glowing brightly in radio wavelengths but remaining completely invisible to optical telescopes. Scientists hypothesize that their luminosity is due to high-energy electrons spiraling through powerful magnetic fields. Nevertheless, their exact nature remains one of astronomy's unsolved mysteries. Radio observations have also revealed a peculiar skeletal structure of gas flows located near the galactic center. Hot ionized gas spirals inward towards the central black hole, forming curved radio arcs that vividly demonstrate the influence of gravitational fields. These gas flows do not fall in a straight line. Instead, they follow complex orbital trajectories, sometimes completing several revolutions around the black hole before finally crossing the point of no return. One of the most impressive radio discoveries was the detection of massive gas clouds being torn apart by the gravity of the central black hole. Astronomers observed in real time as a cloud named G2, containing approximately 3 times the mass of our Earth, was stretched into a long stream as it approached the black hole. Radio emission allowed the disintegration of this cloud to be tracked over several years, providing a unique opportunity to observe gravitational violence on a cosmic scale. Radio waves also indicate the presence of a hot, diffuse atmosphere surrounding the galactic center. This gas has been heated to millions of degrees by shock waves originating from stellar explosions, as well as by energy emanating from the central black hole. Radio emission from this superheated gas creates a luminous halo around the galaxy's heart, observable exclusively by radio telescopes. Perhaps the most outstanding discovery made through radio observations has been the detection of relativistic jets emanating from the galactic center. These are narrow beams of matter and energy that travel at speeds close to the speed of light, ejected outwards by powerful magnetic fields located near the black hole. These jets extend for thousands of light-years above and below the galactic plane, transporting energy and particles far from their origin. Radio signals represent our only way to peer through the dense veil of dust and gas that obscures the galactic center from optical view, opening a window into the most extreme physics laboratory in our galaxy. At the very heart of our galaxy, in a region occupying space smaller than the distance from Earth to our nearest stellar neighbor, reside over 25 million stars. This remarkable nuclear star cluster represents the densest concentration of luminaries in the Milky Way and is one of the most populous places in the entire known universe. If our solar system were located here, the night sky would be illuminated by thousands of stars, shining brighter than our full moon. The stellar density in this region is truly unimaginable. While the nearest star to our Sun is over 4 light-years away, luminaries in the nuclear star cluster can be separated by distances smaller than the size of our solar system. At the very center of this cluster, stellar neighbors can be just a few billion kilometers apart, close enough for their outer atmospheres to interact during close encounters. Planetary systems here would be absolutely impossible. Gravitational chaos would tear apart any orbiting worlds within mere thousands of years. However, these are not just ordinary stars tightly grouped together. Many inhabitants of the cluster are unique stellar exotics, objects that form exclusively under the most extreme conditions. Wolf-Rayet stars are so hot that they eject their outer layers in powerful stellar winds, moving at several thousand kilometers per second. Red supergiants swell to colossal sizes, exceeding Earth's orbit around the Sun. Blue hypergiants shine with the dazzling brilliance of millions of suns, burning through their nuclear fuel so rapidly that they are doomed to explode within a few million years. The gravitational environment here operates under different rules than anywhere else in the galaxy. Stars do not follow simple elliptical orbits like planets around the Sun. Instead, they trace complex rosette patterns as they are pulled by the combined gravity of millions of neighbors and the supermassive black hole at the very center. Some stars move on such elongated orbits that they travel from the edge of the cluster almost to the black hole's event horizon and back. The cluster formed through a process that lasted billions of years. As gas streams spiraled inward toward the galactic center, they triggered powerful bursts of star formation in the dense environment near the supermassive black hole. Over time, these stellar generations grew into the massive cluster we observe today. But star formation here was not a gradual process. It occurred in tumultuous episodes caused by major gas infall events, creating distinct populations of stars with varying ages and compositions. Life cycles here are compressed and accelerated. Massive stars form, live, and die in just a few million years. Their supernova explosions add chaos to this turbulent environment. The cluster contains dozens of stellar mass black holes, neutron stars, and white dwarfs, all packed into the same small volume alongside living stars. When these compact objects collide, they can spiral inward and merge, creating gravitational wave signals that propagate throughout the universe. The nuclear star cluster acts as a natural particle accelerator, using gravitational slingshots to launch stars at incredible velocities. Some stars are ejected from the cluster at speeds exceeding 1,000 kilometers per second, fast enough to completely escape the galaxy. These hypervelocity stars have been detected streaking through the outer regions of the Milky Way, acting as stellar refugees from the gravitational violence of the galactic center. At the cluster's heart lies the source of all this chaos, our galaxy's supermassive black hole. At the very center of our galaxy hides a monster, Sagittarius A. This supermassive black hole at the Milky Way's heart contains a mass equivalent to 4 million suns, compressed into a space smaller than Mercury's orbit. This cosmic giant sits motionless at the galaxy's gravitational center, while 200 billion stars orbit it like moths around a flame. It is the anchor point that holds our entire galaxy together. For decades, astronomers suspected the existence of this monster but couldn't prove it. The galactic center is obscured by vast clouds of dust that block visible light, making direct observation impossible. But in the 1990s, astronomers began tracking individual stars near the galactic center using infrared telescopes, which could penetrate the dust. What they discovered forever changed our understanding of black holes. Stars in the immediate vicinity of Sagittarius A move in elliptical trajectories so extreme that they seem to defy the fundamental laws of physics. One such star, designated S2, completes a full orbit around the giant black hole every 16 years. At its closest approach to the black hole, it hurtles past at a speed exceeding 40 million kilometers per hour, allowing it to cover the distance from Earth to the Moon in just 30 minutes. Gravitational forces at this distance reach such intensity that they cause measurable effects predicted by Einstein's theory of general relativity. However, Sagittarius A is not always dormant. While it appears calm most of the time, the black hole occasionally exhibits bursts of activity when gas or cosmic debris approaches it at a critical distance. These so-called feeding events can increase the black hole's brightness hundreds of times within minutes, as matter spirals inward and heats up to billions of degrees before vanishing forever. The energy released during such flares is capable of outshining all the stars in the nuclear star cluster combined. The black hole's event horizon, that invisible boundary beyond which nothing can escape, has a diameter of about 24 million kilometers. This figure may seem significant, but it is actually tiny compared to the black hole's sphere of influence, which extends for several light-years in all directions. In this vast region, the black hole's gravity dominates everything, controlling the movement of stars, gas clouds, and even light itself. Perhaps the most astonishing discovery concerning Sagittarius A occurred in recent years when astronomers obtained the first direct image of the black hole's shadow. Using a global network of radio telescopes working in sync, they were able to photograph the dark silhouette of the event horizon, surrounded by a luminous ring of superheated gas. This image provided compelling confirmation of decades of theoretical predictions about what black holes should look like. The magnetic field surrounding Sagittarius A is millions of times stronger than Earth's magnetic field. This powerful magnetism accelerates particles to nearly the speed of light and launches them into narrow jets that extend for thousands of light-years above and below the galactic plane. These jets carry energy and matter far from the black hole, influencing star formation processes and gas dynamics throughout the galaxy. Every star in our galaxy, including our Sun, ultimately orbits this central giant. Although we are 26,000 light-years away, Sagittarius A's gravity reaches across the entire galaxy, guiding our motion through space. The black hole's event horizon is the final frontier where space and time themselves break down. We have approached the edge of all existence. Sagittarius A's event horizon marks the boundary where the ordinary rules of physics give way to something incomparably more mysterious. Cross this invisible line, and you will find yourself in a region of space from which nothing, no matter, no light, no information itself, can ever return. It is the ultimate point of no return. A one-way membrane separating our universe from what lies beyond. The event horizon is not a physical surface that one could touch or stand on. It is a mathematical boundary defined by gravity so intense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape once it crosses this line. The horizon appears as a perfect sphere surrounding the black hole, with a diameter of approximately 24 million kilometers. This is large enough to encompass the orbits of Mercury and Venus, if the black hole were located where our Sun is. But here's what's strange. If you somehow approach the event horizon, what you would experience would entirely depend on your perspective. To an external observer tracking your journey, you would appear to slow down as you neared the horizon. Your image would redshift, shifting to progressively longer wavelengths until you vanished from sight, seemingly frozen at the edge of the horizon forever. Time dilation would stretch your final moments into eternity from an outside viewpoint. Your experience would be entirely different. From your perspective, you would pass through the event horizon normally, with no special sensation marking the moment of crossing the point of no return. You might not even realize you had crossed it until you tried to turn around and found that every direction now pointed toward the black hole's center. The horizon would be invisible to you, just empty space that coincidentally possessed a peculiar property. The space in the immediate vicinity of the event horizon undergoes such significant curvature that it completely contradicts our everyday perception of reality. Tidal forces here reach such an extreme magnitude that any object daring to approach too closely would inevitably be stretched and torn apart at an atomic level. This process has been termed spaghettification in astronomical terminology. If a person were in such a situation, their feet would experience a significantly stronger gravitational pull than their head, leading to the body being stretched into a long, thin strand before it was finally destroyed. Time itself behaves extremely unusually near the event horizon. The intense gravitational field causes the passage of time to slow down compared to regions located further from the black hole. Clocks located at the horizon would tick seconds at a different rate than clocks in ordinary space. This phenomenon, known as gravitational time dilation, means that the black hole exists in an entirely different temporal framework than the rest of the galaxy. The horizon also marks the critical boundary beyond which the curvature of spacetime becomes infinite. At the very heart of the black hole lies what physicists call a singularity, a point where density reaches infinite values and all laws of physics, as we currently understand them, completely cease to apply. The event horizon serves as a shield, protecting the rest of the universe from direct contact with this cosmic impossibility. However, recent theoretical investigations suggest that black hole event horizons may not be as absolute as previously thought. Quantum effects arising near the horizon might allow some information to escape through a process known as Hawking radiation. Nevertheless, these effects are so minuscule that they remain undetectable for supermassive black holes like Sagittarius A. Beyond the event horizon lies territory that challenges the very foundations of our understanding of reality. From the supermassive black hole located at the very center of our galaxy, two invisible spheres of energy pierce through space at 99% of the speed of light. These relativistic jets extend for thousands of light-years above and below the galactic plane, carrying matter and energy far beyond the black hole's gravitational grasp. This is one of the most impressive manifestations of cosmic power observed in the universe. What makes them even more remarkable is the fact that they emanate from a region generally believed to allow nothing to escape. In reality, the jets do not originate from within the black hole's event horizon. Instead, they are launched from a spinning accretion disk composed of superheated gas and plasma that spirals towards the black hole. As this material falls inward, it is compressed and heated to billions of degrees, creating conditions more extreme than in the core of any star. Magnetic fields permeating this accretion disk twist and strengthen until they reach sufficient power to launch streams of particles at relativistic speeds. Imagine magnetic field lines as rubber bands being stretched tighter and tighter. Eventually, they snap back with immense force, accelerating charged particles along narrow channels that extend far from the black hole. These jets are incredibly narrow, maintaining their focus for thousands of light years with a precision that would be unattainable by any human technology. The jets from Sagittarius A are relatively weak compared to those emanating from more active supermassive black holes in other galaxies. Some galactic jets are so powerful that they can be detected billions of light years away, outshining all the stars in their host galaxies combined. Our galaxy's central black hole is currently in a quiescent phase, generating jets that are barely detectable even by our most sensitive instruments. But even these faint jets carry a colossal amount of energy. Particles moving along them have been accelerated to energies millions of times greater than anything achievable in human-built particle accelerators. When these high-energy particles interact with magnetic fields or matter in their path, they produce gamma rays, the most energetic form of electromagnetic radiation in the universe. The jets also serve as cosmic particle accelerators, creating some of the highest energy cosmic rays that bombard Earth's atmosphere. These particles move so fast that time dilation effects become very significant. A particle in one of these jets experiences the passage of time much slower than we do. This means its journey across the galaxy takes only minutes or hours from its own perspective, even though thousands of years pass in our reference frame. Recent astronomical observations have revealed the dynamic nature of the jets emanating from Sagittarius A. It has been established that the rotation axis of this supermassive black hole does not remain constant, leading to periodic changes in the direction of the emitted jets. This phenomenon can be compared to water spraying from a rotating sprinkler, continuously altering its trajectory. This procession unfolds over several thousand years, gradually redirecting the energetic jets into various parts of our galaxy. In their motion, the jets actively interact with the surrounding interstellar medium, generating powerful shock waves and heating the gas clouds they encounter. This complex process plays a key role in regulating star formation within the galaxy, as it injects energy into molecular clouds that might otherwise collapse to form new stars. These relativistic beacons represent the most pronounced manifestation of the black hole's influence on its surrounding galaxy, extending its impact far beyond the gravitational prison of the event horizon. In the immediate vicinity of the supermassive black hole located at the very heart of our galaxy, time itself undergoes fundamental changes, becoming not a constant but a variable quantity. The exceptionally powerful gravitational field so significantly warps the fabric of spacetime that an observer notes the slowing down of clocks, the stretching of familiar distances, and the distortion of reality's very essence. These phenomena seem impossible anywhere else in the universe. We find ourselves in a region where Albert Einstein's boldest theoretical assumptions become everyday physical reality. This effect of time distortion, dubbed gravitational time dilation, implies that the passage of time varies depending on how close an object or observer is to the black hole. For example, clocks placed directly beyond the event horizon would tick noticeably slower than identical clocks located in ordinary space. From our perspective, 26,000 light-years away on Earth, these clocks would appear almost frozen, their hands barely moving, as gravity stretches each second into infinity. The effect of time dilation is far from subtle. In the immediate vicinity of Sagittarius A, At the very event horizon of the black hole, time dilation reaches infinity from the perspective of an external observer. This means that any object falling into the black hole would appear to slow down drastically as it approached the horizon. Its image would redshift and dim until it became completely invisible, seemingly frozen at the threshold of eternity. However, time warping extends significantly beyond the event horizon itself. Stars orbiting near the black hole also experience measurable effects of time dilation. Star S2, which we mentioned earlier, completing a full orbit around the black hole every 16 years, actually ages slightly slower than if it were in a more distant orbit. Over millions of years, this difference could amount to thousands of years of additional stellar life. Time warping is inextricably linked to space warping. In the vicinity of a black hole, space itself becomes curved, much like a bowling ball creates a depression on a stretched rubber sheet. This curvature affects not only the flow of time, but also the trajectories that light and matter must follow. Straight lines in ordinary space transform into curved paths near a black hole. One of the most striking consequences of this space-time curvature is the theoretical existence of closed time-like curves. In certain regions adjacent to rotating black holes, it is theoretically possible for a path through spacetime to loop back on itself, potentially allowing for travel into the past. However, these exotic trajectories exist exclusively under the most extreme gravitational conditions and would require survival in an environment that would annihilate any known form of matter. The effects of time dilation near Sagittarius A also influence the light we receive from objects in this region. Radio signals emanating from gas clouds spiraling into the black hole reach Earth with altered frequencies, shifted by the gravitational field. This gravitational redshift provides astronomers with a direct measurement of the black hole's mass and the strength of its gravitational field. Perhaps the most astonishing aspect is that the time warping occurring around supermassive black holes can shed light on some of cosmology's greatest unsolved mysteries. Certain theoretical constructs suggest a close connection between the extreme curvature of the space-time continuum near black holes and the expansion of the universe itself, thereby unifying the most microscopic and the most grandiose scales of cosmic physics. As we move away from this region, where time itself is warped and broken, an understanding emerges of how our entire galaxy is integrated into a significantly larger and more enigmatic structure. Our entire galaxy is embedded within something invisible and mysterious. Surrounding the visible star clusters and gas nebulae of the Milky Way lies a massive spherical halo composed of dark matter. This substance outweighs everything we observe by a factor of 10. This dark halo extends far beyond the galaxy's spiral arms, forming an invisible architecture that holds our cosmic home together and dictates its trajectory through the universe. Dark matter neither emits, absorbs, nor reflects light of any kind. It is utterly invisible to any form of electromagnetic radiation, from radio waves to gamma rays. The only way we can infer its presence is through its gravitational effect on surrounding visible matter. Stars in the peripheral regions of galaxies rotate at higher speeds than they should, based solely on their visible mass. Consequently, something possessing colossal gravitational force must be holding them in their orbits. The Milky Way's dark halo is astonishing in its size, stretching for at least 600,000 light-years from the galactic center. This is 3 times the visible portion of the galaxy, and vast enough to encompass several of our satellite galaxies. If it were somehow possible to observe dark matter, our galaxy would appear as a small, bright disk floating at the center of a much larger and more diffuse sphere. This invisible halo contains approximately 1 trillion solar masses of dark matter, making it the most massive component of our galactic system. All the stars, gas, dust, and planets in the Milky Way, taken together, constitute only about 15% of the total mass. Essentially, we reside within a dark matter structure, with some ordinary matter sprinkled on top, like seasoning on a gigantic cosmic feast. The dark halo is not a perfectly smooth formation. Computer simulations demonstrate that it possesses an internal structure, including clumps and streams of dark matter moving through it. Some of these dark matter clumps may represent the remnants of smaller galaxies that were torn apart by the gravitational influence of the Milky Way billions of years ago. Others could have been primordial structures that formed in the early universe and have persisted to this day. The nature of dark matter remains one of the greatest unsolved mysteries of modern science. Leading candidates include exotic particles that interact solely through gravity and the weak nuclear force, making them virtually undetectable by direct observation. Laboratory experiments worldwide are actively searching for signs of these particles. For now, however, dark matter continues to fully live up to its name. The dark halo also plays a crucial role in the formation and evolution processes of our galaxy. In the early universe, dark matter first condensed, creating gravitational wells that attracted ordinary matter. Gas drawn into these dark matter halos eventually served as the foundation for the formation of the first stars and galaxies. Without the gravitational scaffolding of dark matter, galaxies like the Milky Way would never have been able to form. Our motion through the dark halo generates a cosmic wind of dark matter particles, rushing through the solar system at hundreds of kilometers per second. This dark matter wind is completely imperceptible to our senses. However, it represents one of the most common forms of matter in the universe, streaming past us every second. Beyond our galaxy's dark halo extend even larger structures that surpass anything we've encountered so far. Our galaxy, the Milky Way, is by no means alone in the boundless expanse of space. Surrounding it, like celestial satellites orbiting a giant planet, dozens of smaller galaxies circle. They are gravitational captives, forever locked in an endless dance with our majestic stellar island. These companion galaxies represent diverse formations, from miniature clusters containing only a few million stars to impressive stellar cities harboring billions of luminaries. Altogether, they form a complex gravitational ecosystem that has formed and evolved over billions of years. The most famous of these satellites are the large and small Magellanic Clouds, easily discernible with the naked eye from the southern hemisphere of Earth as hazy patches of light. The Large Magellanic Cloud contains approximately 30 billion stars, which is about 1/10 the mass of the Milky Way. Its smaller companion, the Small Magellanic Cloud, numbers about 3 billion stars, still enough to sustain active star formation and maintain its own internal spiral structure. However, these prominent satellites are just the beginning of an extensive list. Astronomers have already discovered over 50 smaller satellite galaxies orbiting the Milky Way. Among them are those bearing names like Draco, Ursa Minor, and Sagittarius. Most of these are dwarf galaxies, containing from a few thousand to several billion stars. They are scattered across the sky in all directions. Some are very close, at a distance of 75,000 light-years, while others are as far as 3 million light-years from our galaxy's center. The relationship between the Milky Way and its satellites is highly complex and often quite violent. The irresistible gravitational pull of our galaxy literally tears stars and gas away from smaller companions that approach too closely. The Sagittarius dwarf spheroidal galaxy is currently undergoing such a process, leaving behind long streams of stars scattered across our sky. Over hundreds of millions of years, these stellar streams will be completely absorbed by the outer regions of the Milky Way. Some of the satellite galaxies show clear signs of multiple star formation episodes that were triggered by their close encounters with our galaxy. As they move along their elliptical orbits, gravitational forces compress their internal gas clouds, leading to powerful bursts of new stellar birth. These interactions form irregular patterns of stellar ages within the satellites, much like geological layers record their orbital history. Satellite galaxies also serve as unique laboratories for studying dark matter. Many of these small galaxies appear to be dominated by dark matter, with visible stars making up only a tiny fraction of their total mass. Some satellites are so rich in dark matter that they barely have enough ordinary matter to initiate star formation processes, existing as invisible gravitational ghosts with only a handful of stars indicating their presence. The distribution of satellite galaxies around the Milky Way is not random. They tend to be arranged in a flattened, disk-like structure rather than being spherically scattered around us. This unexpected pattern has challenged our understanding of how galaxy groups form and evolve, suggesting that the early universe may have possessed a more complex structure and organization than previously thought. Our satellite system is constantly changing as new members are discovered and existing ones are torn apart by tidal forces. Recent studies have revealed extremely faint satellite galaxies, barely brighter than large star clusters, pushing the boundaries of what we consider a true galaxy. But even our impressive collection of satellite galaxies pales in comparison to the streams of gas and debris flowing between them. Beyond the Magellanic Clouds, like a cosmic contrail, stretches one of the largest structures associated with our galaxy. The Magellanic Stream is a gigantic river of hydrogen gas that extends for over 600,000 light-years across our sky, longer than the diameter of our entire galactic disk. This enormous flow of material tells the story of a slow-motion collision that has unfolded over billions of years. The stream was formed by galactic-scale gravitational theft. As the large and small Magellanic Clouds orbit our galaxy, the Milky Way's superior gravitational pull rips away their outer layers of gas and stars. This stolen material does not fall directly into our galaxy. Instead, it is stretched into long tidal tails that trace the Magellanic Cloud's orbital path through space. But the Magellanic Stream is far more than just a single trail of cosmic debris. Recent astronomical observations have revealed that it is actually a complex, multi-dimensional network of gas flows. Some of these streams are heading towards the Milky Way, while others, conversely, are being ejected outwards, carried into the boundless expanses of intergalactic space. The gravitational interaction between the large and small Magellanic Clouds, our galaxy's satellites, significantly amplifies this complexity. As these two satellite galaxies actively tear material from each other, while simultaneously losing gas under the powerful tidal forces of our Milky Way, the stream accumulates enough substance to form 2 billion stars comparable in mass to our Sun. This is a colossal amount of gas, exceeding the volumes present in many entire galaxies. And all this immense accumulation is stretched across hundreds of thousands of light-years of space. As this material gradually falls into the Milky Way over the next few billion years, it will undoubtedly trigger new episodes of intense star formation across our galactic disk. What makes the Magellanic Stream even more astonishing is its unique chemical composition. The gas torn from the Magellanic Clouds contains significantly fewer heavy elements compared to the material found in our own galaxy's disk. When this relatively pristine gas mixes with the Milky Way's already processed material, it effectively dilutes the concentration of heavy elements while simultaneously providing fresh fuel for the star formation process. This continuous gas recycling helps explain why our galaxy is capable of continuing to form new stars for billions of years after its initial formation. Furthermore, the stream contains dark matter, which was also stripped from the Magellanic Cloud's halos. This invisible component plays a crucial role in helping to bind the gas flows together and significantly influencing their orbital dynamics. Computer simulations convincingly demonstrate that dark matter streams, formed during the disruption of satellite galaxies, may well be responsible for some of the substructures found in our galaxy's dark matter halo. The Magellanic Stream is just one of many vivid examples of the ongoing merger and accretion processes that have shaped our galaxy throughout its cosmic history. Similar streams, composed of debris from other disrupted satellite galaxies, traverse the outer regions of the Milky Way, providing undeniable evidence that galaxy formation is a continuous process, not a one-time ancient event. However, all these gradual changes pale in comparison to the grand cosmic collision that awaits us in the future. Approximately 4.5 billion years from now, our night sky will be transformed beyond recognition. The Andromeda Galaxy, currently hurtling towards us at 400,000 kilometers per hour, will collide with the Milky Way in the most spectacular cosmic event our galaxy will ever experience. This colossal impact will reshape both galaxies, flinging stars onto entirely new orbits and potentially triggering the largest burst of star formation in each galaxy's history. Let the word collision not be misleading. When galaxies collide, individual stars almost never crash into each other. The distances between stars are so immense that most will pass through the chaos without any direct impact. Instead of direct stellar contact, this is a monumental clash of gravitational fields, gigantic gas clouds, and vast dark matter halos. The overall structure of both galaxies will be completely transformed, but the process itself will unfold over hundreds of millions of years. Andromeda is the largest galaxy in our local group, containing approximately 1 trillion stars, while our galaxy numbers about 400 billion. It is also approaching us almost head-on, which will make the collision even more dramatic than if the galaxies were to graze each other. Computer simulations show that the initial impact will fling streams of stars into intergalactic space, creating spectacular tidal tails hundreds of thousands of light-years long. The supermassive black holes located at the centers of both galaxies will eventually begin to spiral toward each other, creating one of the most energetic events possible in the universe. As these cosmic monsters orbit closer and closer, they will generate gravitational waves that will ripple through space-time itself. The final merger of the black holes will release more energy in the form of gravitational waves than all the stars in both galaxies combined produce in light. Our solar system will likely survive this cosmic rearrangement, although our location within the galaxy will most probably change dramatically. The Sun and its planets might be flung into the outer regions of the merged galaxy, or we could find ourselves significantly closer to the new galactic center. The good news is that by the time of this collision, the Sun will already be entering its red giant phase. Thus, Earth's habitability will already be threatened by the natural evolution of our star. This monumental cosmic collision will undoubtedly trigger powerful bursts of star formation as gas clouds from both galaxies come into contact and undergo intense compression. These flares of new stellar birth will illuminate the merged galaxy with the dazzling brilliance of billions of young stars, transforming it into one of the brightest objects in our local universe. The rate of star formation could increase hundreds of times compared to current figures. Astronomers have already given this future merged galaxy a name, Milky Way. Most likely, it will take the form of an elliptical galaxy rather than a spiral one, as the grand collision will disrupt the ordered rotational patterns that maintain a spiral structure. The new galaxy will surpass either of its parent galaxies in size and mass, containing the combined stellar populations of both the Milky Way and Andromeda. But even this cosmic catastrophe represents just one phase in the long-term evolution of our galactic home. As larger forces continue to shape the universe around us, the story of our galaxy will not have a happy ending. Over timescales so vast they dwarf the current age of the universe, the Milky Way will gradually fade as its stars burn out one by one, leaving behind a cold, dark graveyard of stellar corpses drifting in an ever-expanding cosmos. The death of our galaxy will unfold over trillions of years, but the process has already begun. The first stage of galactic death is already underway. The rate of star formation in our galaxy has been declining for billions of years as fresh gas supplies deplete. Most of the hydrogen and helium available for new stars has already been consumed or ejected from the galaxy by stellar winds and supernova explosions. Approximately 10 billion years from now, the Milky Way will completely cease forming new stars, becoming what astronomers call a red and dead galaxy. As star formation ends, the galaxy's population will age dramatically. Massive bright blue stars that currently dominate stellar nurseries will have long since exploded as supernovae. Medium-sized stars like our Sun will transform into red giants, then shed their outer layers and become white dwarfs. the galaxy will gradually grow redder and dimmer, as only the longest-lived, smallest stars continue to burn. Red dwarfs, the most common type in our galaxy, can burn for trillions of years. These tiny, cool stars will be the last lights shining in the aging Milky Way, providing faint illumination across cosmic timescales that defy human imagination. But even these stellar survivors will eventually exhaust their nuclear fuel and fade into brown dwarf remnants. The supermassive black hole at our galaxy's center will play an increasingly important role as the galaxy ages. Without an influx of fresh gas to fuel star formation, material will gradually spiral inward toward the central black hole. Stars that approach too closely will be torn apart by tidal forces, briefly flaring as their material is consumed. Eventually, the black hole will swallow a significant portion of the galaxy's remaining mass. On even longer timescales, the expansion of the universe itself will begin to tear our galaxy apart. Dark energy, the mysterious force driving cosmic acceleration, will eventually overcome the gravitational forces holding the Milky Way together. Individual star systems will be carried away from each other by the expanding fabric of space itself. The final chapter in our galaxy's history involves the evaporation of remaining black holes via Hawking radiation. This quantum mechanical process causes black holes to slowly lose energy and shrink over periods measured in Google years. The numbers are so vast that they are written with more zeros than there are atoms in the observable universe. When the last black hole evaporates, it will mark the end of the Milky Way's existence. But perhaps death isn't quite the right word for this cosmic transformation. The matter and energy that once comprised our galaxy will persist in new forms, possibly contributing to the formation of entirely different structures in a universe we can barely imagine. Carbon, oxygen, and other heavy elements forged in our galaxy's stars will continue to exist, potentially serving as building blocks for whatever comes next in cosmic history. Nevertheless, even in its ultimate fate, our galaxy remains part of something far grander and more immense. The Milky Way is undoubtedly impressive in its splendor, but it hardly compares to some galactic giants lurking in the boundless depths of the universe. Scattered across the cosmos are galactic monsters so colossal that our home seems like no more than a cosmic minnow in comparison. These behemoths of the universe contain hundreds of trillions of stars, stretch for millions of light-years, and conceal black holes whose masses are so great they could swallow our entire solar system millions of times over. The largest known galaxy is IC 1101. This giant elliptical galaxy spans over 5 million light-years from one edge to the other. To grasp this scale, suffice it to say that the distance from our galaxy to Andromeda could fit